Were the legendary Tiger tanks truly the ultimate Wehrmacht armor or surprisingly overrated? Compare the battlefield performance of Sturmgeschütz III, Panzer IV, Panther tank, and the Tiger through actual combat data and historical accounts. This military history compilation deep dive examines the engineering strengths and critical flaws of these iconic World War II vehicles that continue to fascinate enthusiasts today. March 1943, near Kharkov. SS Hauptsturmführer Kurt Knispel, commanding a Sturmgeschütz III, destroyed 5 Soviet T-34s in under 3 minutes. Armed with the powerful 75mm StuG III-40L/48, the vehicle's low profile and deadly accuracy made it the Wehrmacht's most efficient tank killer. With over 20,000 confirmed enemy tank kills, the Sturmgeschütz III wasn't just a support gun, it became the backbone of German armored defense. Discover why General Feldmarschall Model insisted on Sturmgeschütz for his 9th Army. Its 75mm StuG III-40L/48 main gun represented a dramatic evolution from the original short-barreled L/24 howitzer. When General Oberst Heinz Guderian submitted his assessment of early war operations to OKH in December 1941, he specifically noted, "Our assault guns lack sufficient penetration against the T-34. Chief designer Walter Roland at Alket responded by adapting the longer KWK-40 tank gun, creating the purpose-built StuG-40 with its distinctive muzzle brake and semi-automatic vertical sliding breech block. This gun fired the PZGR-39 armor-piercing round at 790 meters per second, achieving 91mm penetration at 1,000 meters, sufficient to defeat a T-34's frontal armor at combat ranges. The gunner, positioned on the right side of the fighting compartment, utilized the SFLZ-F1 gun sight with its 5x magnification and 8-degree field of view, allowing precise targeting at ranges exceeding 1,500 meters. Ammunition stowage underwent continuous refinement throughout production. Early AOSF-F models carried 44 rounds, while the AOSF-G increased capacity to 54 projectiles, with ready racks positioned for optimal loader access. The loader, standing to the left of the breech, could achieve 6 to 8 rounds per minute in combat conditions. Slower than turreted tanks, but compensated by superior first-hit probability due to the vehicle's low silhouette. The Sturmgeschütz's armor protection demonstrated German pragmatic engineering. The frontal glacis plate measured 80 millimeters thick at 30 degrees in late production models, offering effective protection against the Soviet 76.2mm F-34 gun at ranges beyond 500 meters. Side armor remained relatively thin at 30 millimeters, necessitating careful tactical employment. Unlike turreted tanks, the StuG presented a significantly reduced target profile, just 2.16 meters in height compared to the Panzer IV's 2.68 meters, translating to approximately 40% less frontal area exposed to enemy fire. General Feldmarschall Walter Model, commanding 9th Army during Operation Citadel, specifically requested Sturmgeschütz IIIs for his formations due to this survivability advantage. General Major Horst Grossmann of the 6th Infantry Division reported after the battles near Orel, "Our StuG survived direct hits that would have destroyed conventional tanks." The vehicle's Maybach HL120 TRM engine, producing 300 horsepower at 3,000 RPM, powered the 23.9-ton StuG III AOSF-G to a maximum road speed of 40 kilometers per hour. However, its practical cross-country speed rarely exceeded 15 to 20 kilometers per hour. The transmission, a 6-speed ZFSS G77 with 1 reverse gear, was known for its reliability, but required skilled drivers. The final drive ratio of 5.29 to 1 balanced acceleration with top speed effectively. Fuel capacity of 320 liters provided an operational range of approximately 155 kilometers on roads, inadequate for Eastern Front operations. Field modifications frequently included mounting additional fuel drums on the rear deck, a practice standardized in later production models. Tank Commander Hauptmann Hans Bolter noted in his after-action report following operations in Ukraine, "The limited fuel capacity forces constant resupply, limiting our operational flexibility." The torsion bar suspension system, inherited from the Panzer III chassis, utilized 6 small road wheels per side with 3 return rollers. This system provided acceptable cross-country performance, but proved vulnerable to freezing in Russian winters. Maintenance crews developed special procedures detailed in the Ausführung G maintenance manual issued by Alcott in late 1943, requiring periodic cycling of the suspension in extreme cold to prevent seizure. Communication equipment evolved significantly throughout production. Early models utilized the FuG-5 radio with a range of approximately 3 kilometers, later upgraded to the FuG-16 with improved reliability and range up to 8 kilometers. The four-man crew configuration, commander, gunner, loader, driver, in standard models created significant communications challenges within the vehicle, especially during combat operations. The addition of a dedicated loader in all StuG III variants was standard from the beginning. The Sturmgeschütz's tactical employment transformed dramatically throughout the war. Originally conceived as infantry support platforms under the direction of General Erich von Manstein, they evolved into primary tank destroyers under General Heinz Guderian's guidance. By 1944, dedicated StuG battalions, Sturmgeschützabteilungen, were employing specific tactics developed by Major Ernst von Jungenfeld, emphasizing concealment, ambush, and coordination with infantry screens. Production efficiency represented one of the StuG's greatest strengths. Reichsminister Albert Speer's streamlining efforts reduced production time from 5,500 man-hours in 1942 to just 2,800 by early 1944. Manufacturing costs averaged 82,500 Reichsmarks per vehicle, approximately 45% less than a Panzer IV, while maintaining superior combat effectiveness. This efficiency allowed Germany to produce 10,500 units, despite increasing resource constraints. The Sturmgeschütz's combat record confirms its effectiveness. According to Wehrmacht records analyzed by historian Franz Wilhelm Lochmann, StuG III's accounted for approximately 20,000 enemy tank kills throughout the war, at a remarkably favorable exchange ratio. During the battles around Lake Balaton in March 1945, a single StuG battalion under Obersturmbannführer Otto Skorzeny claimed 45 Soviet tanks destroyed while losing only 8 vehicles. Technical limitations became increasingly apparent as the war progressed. The fixed superstructure limited traverse to just 20 degrees, 10 degrees left and right, forcing the entire vehicle to rotate for larger adjustments, a significant disadvantage in fluid combat situations. Commander Otto Carius, who served in both StuG and Tigers, wrote, "The Sturmgeschütz demands perfect position selection before engagement, as it cannot quickly shift targets across a wide arc. The crew compartment's confined space, just 4.5 cubic meters, created significant ergonomic challenges, especially during prolonged operations. The commander's vision was limited to a single SF-14Z periscope and a commander's cupola with 5 vision ports, creating dangerous blind spots. This limitation was partially addressed in late 1944 with the addition of side-mounted Nahverteidigungswaffe, close defense weapons, to counter infantry attacks. The StuG III represents a masterclass in practical combat engineering, trading theoretical tank design ideals for battlefield pragmatism. Its combination of potent firepower, minimized silhouette, simplified production, and tactical flexibility made it Germany's most cost-effective armored fighting vehicle. As Generaloberst Heinz Guderian noted in his final wartime report, "Had we concentrated entirely on Sturmgeschütz production rather than numerous specialized vehicles, our armored capabilities would have been significantly enhanced." What made Panzer IV a blitzkrieg game-changer? Designed in 1937 as an infantry support platform, the Panzerkampfwagen IV, Panzer IV, underwent significant evolution from the Ausf-D to the Ausf-J, reflecting a series of calculated enhancements aimed at countering the formidable T-34 and M4 Sherman. Initially, the AOS-V-D featured 20 mm side armor and a 75 mm KWK-37L/24 gun, effective against infantry but inadequate against the T-34's sloped armor. Subsequent models saw frontal armor increase to 80 mm and the adoption of the longer 75 mm KWK-40L/48 gun, enhancing anti-tank capabilities. In contrast, The T-34 maintained superior mobility with its wide tracks and Christie suspension, and its 76.2mm F-34 gun remained effective throughout much of the war. The M4 Sherman balanced firepower and mobility, but faced challenges against upgraded Panzer IVs. Ultimately, while the Panzer IV's incremental improvements enhanced its combat performance, they could not fully mitigate the advantages held by the T-34 and Sherman in terms of mobility and production efficiency. The Panzer IV's chassis featured a compact, welded hull designed to optimize mass distribution. Early models used 10 to 30mm armor, later augmented to 50mm in frontal sections for enhanced survivability. Field crews sometimes retrofitted additional steel plates to vulnerable lower sections, countering the impact of Allied 75mm rounds. The turret, engineered with a low-profile design, utilized an 80mm frontal armor plate in advanced variants and minimized target silhouette while integrating a hydraulically assisted traverse mechanism for rapid engagement. Manufactured with precision, the Panzer IV's armor plates were rolled homogeneous steel, then welded into a monocoque structure. This approach reduced production time and ensured uniformity across units, although early weld seams were occasionally vulnerable to concentrated high-velocity impacts. Refinements in welding methods eventually improved structural continuity and resistance. Later variants incorporated turret and hull-mounted smoke dischargers to obscure targeting, while refined camouflage schemes minimized visual detection. Upgraded self-sealing fuel tanks reduced fuel spillage by roughly 40%, significantly diminishing post-hit fire hazards. Internally, a 5-man crew was allocated within a compact, functionally segmented space. The driver, gunner, loader, commander, and radio operator benefited from an optimized layout that minimized movement delays and improved communication under combat stress, directly contributing to the tank's operational efficiency on the battlefield. The internal layout segregated the fighting compartment from ammunition storage, with blast-resistant bulkheads shielding critical areas. This design, coupled with improved ventilation and overpressure relief systems, effectively mitigated the risk of internal explosions under enemy fire, ensuring enhanced crew survivability in prolonged engagements. Can refined design and raw power tip the scales of war? The Maybach HL120 is a 12-cylinder, 21.4-liter gasoline engine, delivering roughly 300 horsepower at around 3,000 revolutions per minute. Its robust design ensured steady torque output, achieving a power-to-weight ratio of approximately 12 horsepower per ton for a 25-ton chassis, critical for maintaining momentum during sustained operations. Coupled with a 6-speed transmission and single reverse gear, the engine's output was efficiently managed across varied terrains. The tank's torsion bar suspension, paired with overlapping road wheels, absorbed shocks while preserving track alignment. Reinforced, articulated steel tracks provided exceptional grip on mud and uneven ground, minimizing slippage and wear under combat stress. Capable of reaching up to 40 kilometers per hour on roads and maintaining steady cross-country movement, the Panzer IV's mobility was optimized for rapid repositioning. Although Allied vehicles like the M4 Sherman featured higher power outputs, the Panzer IV's balanced drivetrain and durable suspension offered reliable, enduring performance in diverse operational theaters. Wehrmacht maintenance records indicate an operational availability exceeding 70%, while crew accounts highlight its mechanical endurance and straightforward field repairs. The early 75mm KWK-37 featured a short-barrel L-24 delivering a muzzle velocity near 600 meters per second, firing both high-explosive and armor-piercing rounds. Its design suited early war engagements, but as Allied armor thickened, the upgrade to the 75mm KWK-40L/48 became imperative. The extended barrel increased muzzle velocity to roughly 800 meters per second, with APCBC rounds capable of penetrating up to 120 millimeters of armor at 1,000 meters, marking a decisive leap in anti-tank performance. The tank's coaxial MG-34, 7.92 millimeters, provided continuous anti-infantry cover at roughly 800 rounds per minute, while select variants featured a turret-mounted MG-42, delivering rapid suppression during close combat engagements. A fixed optical sight with a simple reticle enabled quick target acquisition, optimized for 300 to 500 meter engagements. Manual traverse and elevation adjustments allowed operators to maintain a steady rate of fire, typically 8 to 10 rounds per minute, even under battlefield stress. The StuG-5 radio system enabled voice communication up to 2 to 3 kilometers, allowing coordinated breakthroughs and encirclements. Engineered for excellence, but would its might survive war's ultimate trial? The Panzer IV's engagement in the Battle of Kursk in 1943 highlighted both its strengths and limitations. While the tank's firepower was effective, the battlefield's terrain and the presence of advanced Soviet armor necessitated continuous tactical adaptations. Throughout 1943, German forces lost approximately 2,352 Panzer IVs on the Eastern Front, underscoring the intense combat conditions and the tank's pivotal role. In the lead-up to D-Day, Panzer IVs constituted about half of Germany's tank strength on the Western Front. The bocage terrain of Normandy favored defensive operations, allowing German tanks and anti-tank guns to inflict significant casualties on Allied armor. However, the dense hedgerows also hindered tank maneuverability, leading to challenges in offensive operations. The side skirts of the Panzer IV, designed to counter shape-charge anti-tank weapons like the British PIAT, were often torn off during movement through dense terrain, reducing their effectiveness. Following the Allied invasion, the Panzer IV continued to serve as a backbone for German armored divisions. However, the increasing prevalence of Allied tanks equipped with more powerful guns, such as the American M4 Sherman with the 76mm gun and the British Firefly with the 17-pounder, posed significant threats. Despite these challenges, the Panzer IV's 80mm frontal hull armor provided resilience against many Allied anti-tank weapons, though the turret remained a vulnerable spot. The Panzer IV's evolution throughout World War II reflects a balance between innovation and adaptation. Its initial design shortcomings were addressed through continuous modifications, allowing it to remain a formidable presence on the battlefield. However, as Allied forces adapted and introduced more advanced weaponry, the Panzer IV's limitations became more pronounced. Understanding the tank's operational history provides valuable insights into the dynamics of armored warfare and the complexities of military innovation under combat conditions. Why Tigers were the most feared tanks in World War II, and why did Germany develop new heavy tanks in the first place? The appearance of heavily armored Allied tanks like the Soviet T-34 and KV-1 outmatched existing German armor. But how did Germany respond to this challenge? They initiated the development of the Tiger I to counter these superior Soviet designs. However, what was the outcome of this development? The Tiger I entered service in 1942, providing Germany with a formidable heavy tank. Yet, why was there a need for a successor to the Tiger I? The evolving battlefield and advancements in Allied armor necessitated an even more powerful tank. So, what was Germany's solution? They developed the Tiger II, also known as the King Tiger, which featured enhanced armor and firepower. But how did these tanks impact German armored strategy? The Tigers became central to Germany's efforts to regain armored superiority during the war. However, what challenges did they face in production? The complexity and resource demands of these tanks limited their production numbers. So, what was the ultimate effect of these limitations? Despite their battlefield prowess, the limited numbers of Tiger tanks constrained their overall impact on the war's outcome. But what made the 88mm gun such a formidable weapon in World War II? Originally designed as an anti-aircraft gun, its high velocity and ability to pierce thick armor made it perfect for use in the Tiger tanks. But how did this adaptation impact its performance against enemy tanks? The gun's ability to fire high-velocity rounds allowed it to engage Allied tanks at significantly greater ranges, often before they could retaliate. However, how did this compare to the armament of other tanks at the time? The 88mm gun far outclassed most other tank guns, including those on the Soviet T-34 and American Sherman, in terms of both range and penetration. Yet, how did this heavy firepower affect the tactics of both the German and Allied forces? Allied forces quickly realized they had to avoid direct engagements with Tigers, often relying on ambush tactics or air support to neutralize them. Then how did the psychological effect of the 88mm gun impact morale on both sides? The sheer reputation of the Tiger's firepower demoralized Allied troops, who were often forced to retreat or alter their strategies when encountering these tanks. However, what about the German crews operating these guns? While the firepower was awe-inspiring, the limited number of Tigers in service meant that crews faced constant pressure to maximize their tanks' effectiveness on the battlefield. So, how did the Allies attempt to counter this overwhelming firepower? They developed more advanced anti-tank weapons and began focusing on coordination between infantry, armor, and air support to neutralize the Tigers. Yet despite these efforts, what lasting impact did the Tiger's firepower have on tank warfare? The Tiger's 88mm gun forced a rethinking of tank and anti-tank designs, influencing tank tactics for decades after the war. What made the armor of the Tiger tanks so remarkable? The Tiger tanks were equipped with incredibly thick armor, with the front plate reaching up to 100 millimeters, offering exceptional protection. But how did this thickness compare to other tanks at the time? The Tiger's armor was considerably thicker than most other tanks, such as the Soviet T-34, which had much thinner plates, making it far more resistant to enemy fire. However, why did the designers choose to focus on thickness rather than using sloped armor? German engineers opted for vertical armor, believing that thick plates would provide better protection against the high-velocity rounds they expected from Allied tanks and anti-tank guns. Then did this lack of sloping affect the Tiger's overall defensive capabilities? Despite not using sloped armor, the Tiger's thick frontal armor was still highly effective in deflecting or absorbing incoming shots, leading to the perception that sloping was unnecessary in this design. Yet, how did this design choice impact the tank's mobility? The heavy armor made the Tiger relatively slow and cumbersome, often limiting its operational range and mobility on the battlefield. So what challenges did the Allies face when attempting to counter this advanced armor? Allied forces had to develop new anti-tank weapons, including larger caliber guns and specialized ammunition, to penetrate the Tiger's formidable armor. However, how did the armor influence the psychology of both sides? The presence of the Tiger instilled fear in Allied forces, who often avoided direct confrontations, while the Germans relied on the tank's superiority to intimidate and dominate in battle. What suspension system did the Tiger tanks use? The Tiger tanks employed a torsion bar suspension system, which provided improved stability and mobility on rough terrains. But how did this affect the Tiger's ability to navigate the battlefield? The torsion bar system allowed the heavy Tiger tank to maintain better track contact even in difficult environments, enhancing its operational range. However, what made the system superior to alternatives at the time? Unlike other tanks that relied on volute spring suspensions, the Tiger's torsion bar system provided superior weight distribution and handling. Yet, how did the heavy weight of the Tiger impact its overall design? The weight required additional innovations like reinforced shock absorbers on the suspension to prevent damage during cross-country movement. So how did these shock absorbers influence the tank's performance? They helped maintain consistent suspension functionality, even in rough terrain, allowing the Tiger to maintain speed and maneuverability. Then, how did this advanced suspension system compare to other tanks' battlefield performance? The Tiger's system provided an advantage in speed and mobility, allowing it to better absorb the impacts of uneven terrain and keep firing steadily. What role did optical systems play in the Tiger's combat effectiveness? The Tiger tanks were equipped with precision optics, such as the Turmzielfernrohr 9B sight, which offered improved targeting accuracy. But how did this optical advantage translate to battlefield success? It allowed gunners to engage targets from greater distances, often before their opponents could react, giving the Tiger a distinct edge in ranged combat. However, was this optics system unique to the Tiger? While advanced optics were present in other tanks, the Tiger's sights were among the best of their time, providing exceptional clarity and magnification. Yet, how did this affect the strategy and tactics employed by crews? The advanced sighting system allowed for greater tactical flexibility, as crews could engage and destroy enemy tanks with greater precision and from further away. So, what did this mean for the tank's survivability? The ability to strike first at longer ranges often meant fewer retaliatory hits from enemies, contributing to the Tiger's formidable reputation. In conclusion, the Tiger's advanced suspension and optical systems played a key role in its battlefield superiority, providing both mobility and precision, and setting a new standard for armored warfare design. How did the German military initially deploy Tiger tanks during World War II? How did the German military initially deploy Tiger tanks during World War II? The German military first deployed Tiger tanks in 1942, particularly in the Battle of Operation Torch in North Africa, aiming to provide a decisive edge over Allied forces. But what challenges did they face in these early deployments? The desert's harsh conditions, with its dust and extreme temperatures, caused frequent mechanical failures, limiting the tank's effectiveness and operational range. Yet, how did the German military respond to these mechanical setbacks? They established forward maintenance units and dedicated repair facilities to ensure that Tigers could be kept in operational condition despite the environmental challenges. However, did these solutions fully resolve the operational difficulties? Despite the maintenance efforts, the Tiger's mechanical issues remained a significant concern, and the tank's slow mobility continued to hinder their full potential in the field. Then how did the German military adapt their strategy in battles with more favorable terrain? In battles like Kursk, the Germans exploited the open, flat terrain, allowing the Tigers to maximize their long-range firepower and reduce the risk of close-range combat. But how did the Battle of Kursk specifically highlight the strengths of the Tiger tanks? The Tiger's heavy armor and high-velocity 88mm gun were key to breaking through Soviet defensive lines and providing decisive support for German infantry. Yet despite these strengths, how did the Germans adapt their tactics for urban environments like in the Battle of Normandy? Urban combat presented unique challenges, where narrow streets and dense buildings required Tigers to be employed cautiously, with infantry support to clear obstacles and protect the tank's flanks. So, how did the Allies adjust to the deployment of Tiger tanks in Normandy? Allied forces began using combined arms tactics, focusing on coordinated infantry and tank ambushes, along with airstrikes, to neutralize the heavily armored Tigers. But what was the psychological effect of encountering these imposing machines on both sides? The reputation of the Tiger tank alone often instilled fear in Allied troops, leading them to alter their tactics, while German crews took advantage of this psychological edge to dominate engagements. Then how did the Germans address the limited number of Tigers available? With relatively few Tigers in service, they were strategically deployed in high-priority battles, maximizing their impact in critical areas like defense or counteroffensive operations. However, despite their tactical advantage, what lessons did the German military learn from deploying Tiger tanks? The Germans learned that while the Tiger's firepower and armor were impressive, without proper logistical support and adequate coordination with other units, the tank's strengths could be undermined. Then, how did the Tiger's mechanical and fuel challenges impact its deployment? These issues necessitated extensive logistical support and maintenance, often limiting the number of Tigers available for combat at any given time. However, were there any design features intended to mitigate these challenges? The Tiger was equipped with a robust suspension system and reinforced components to handle its weight, but these measures were insufficient to fully address its mechanical and fuel-related problems. So how did the German military adapt to these limitations? They implemented specialized maintenance units and recovery vehicles to support the Tigers, but the persistent mechanical issues continued to strain resources. Yet despite these challenges, how did the Tiger tanks influence tank design? The Tiger's performance highlighted the importance of balancing firepower, armor, and mobility, influencing future tank development strategies. In conclusion, how did the Tiger's mechanical challenges affect its legacy? While the Tiger tank was formidable on the battlefield, its mechanical and logistical limitations ultimately constrained its effectiveness and production numbers, leaving a complex legacy in armored warfare history. What were the initial Allied responses to the formidable Tiger tanks? The Allies quickly recognized the Tiger's superiority and began developing specialized anti-tank weapons, such as the British 17-pounder and the American 76mm gun, to counter its heavy armor. However, how did these new weapons perform against the Tiger? Despite their increased firepower, these weapons often struggled to penetrate the Tiger's thick armor at standard combat ranges, necessitating tactical adjustments. Then, what tactical changes did the Allies implement to overcome this challenge? Allied forces adopted ambush tactics, utilizing terrain and coordinated attacks to target the Tiger's weaker spots, such as the rear and tracks. Yet, how effective were these ambush tactics in practice? While ambushes increased the likelihood of disabling or destroying Tigers, the success rate varied, and the risk to Allied crews remained high. So did the Allies develop any specialized vehicles to assist in combating the Tiger? Yes, the British introduced the Sherman Firefly, a modified M4 Sherman tank equipped with a 17-pounder gun, enhancing its anti-tank capabilities. However, were these specialized vehicles widely available? Due to limited production and resources, the number of specialized anti-tank vehicles was insufficient to equip all units, leading to reliance on standard tactics. Then how did the Allies address the psychological impact of facing the Tiger? The Allies conducted extensive training to boost morale and prepared crews to face the Tiger with confidence, emphasizing tactical proficiency over technological disparity. Yet, did these psychological strategies always succeed? Despite training, the presence of Tigers often instilled fear and hesitation among Allied troops, affecting combat effectiveness. When Soviet tank crews first encountered the Panther on the Eastern Front in 1943, fear swept through their ranks. The Panther's sloped frontal armor, capable of deflecting even the formidable 76.2mm shells of the T-34, combined with its powerful 75mm KWK-42L/70 gun, gave it a deadly advantage at long ranges. Its debut at the Battle of Kursk, despite initial mechanical issues, marked a new chapter in tank warfare. Reports of Panthers knocking out Soviet T-34s from over 1,500 meters began to circulate among Soviet intelligence. These accounts intensified after field actions like those of Panther crews from the 2nd SS Panzer Division Das Reich, who during the 1944 Normandy campaign executed textbook long-range ambushes against British armor, including Shermans and Fireflies, near Caen. The Panther's sleek silhouette and fearsome capabilities turned it into a battlefield legend, less a tank, more a stalking predator evolved for one purpose: domination. Yet this German superweapon harbored fatal flaws that would ultimately doom it. Beneath its fearsome exterior lurked a web of catastrophic engineering compromises that transformed Germany's supposed war winner into a strategic liability. Let's dissect the Panther's fatal flaws. The Panther's transmission system represented one of its most critical weaknesses. Developed by engineers at ZF Friedrichshafen, the ZF AK-7-200 gearbox attempted to solve the fundamental challenge of transmitting 700 horsepower to 45 tons of steel. During field exercises at Kummersdorf Proving Grounds in February 1943, test drivers reported alarming failures. Final drives regularly broke down after just 150 kilometers of operation. The root cause was not material quality but fundamental engineering. The planetary gears measured only 250 millimeters in diameter, nearly identical to those used in the much lighter Panzer IV, creating enormous stress concentrations during turning maneuvers. Oberst Hermann Balck, commanding a Panther battalion in the Großdeutschland division, logged these failures meticulously. His records show a significant number of early Panthers became non-operational due to transmission failures during Operation Citadel, never encountering enemy fire. The 80mm thick frontal glacis plate proved irrelevant when most tanks couldn't reach the battlefield. This engineering compromise stemmed directly from production constraints at Daimler-Benz and MAN facilities. When General Inspecteur der Panzertruppen Heinz Guderian inspected production lines in December 1942, he demanded an immediate deployment despite technical engineers' objections about inadequate testing. As a result, early models featured single-stage planetary gears to simplify production, saving time but catastrophically reducing durability. The Maybach HL-230P30 engine itself represented another paradox of excellence undermined by practicality. Chief Engineer Karl Maybach designed the 700 horsepower V12 with performance parameters exceeding contemporary Allied power plants, but its tolerances proved unsuitable for frontline maintenance. The engine required high-quality lubricants, increasingly unavailable after Allied bombing and material shortages. Maintenance records from the 11th Panzer Division show average engine life declining from 1,500 kilometers in mid-1943 to just 800 kilometers by early 1944. General Guderian wrote in his memoirs, "The Panther was a superb fighting machine when operational, but maintaining it in combat conditions proved nearly impossible." This assessment was validated through battlefield recovery data. Approximately 38% of Panthers abandoned during the Normandy campaign suffered mechanical failures rather than combat damage, according to reports from the 21st Panzer Division under Oberstleutnant Wilhelm von Schöller. The fuel system presented another critical vulnerability. Tank designer Ernst Kniepkamp prioritized performance over reliability, implementing a pressurized fuel injection system that boosted horsepower but required precision maintenance. Technical service reports from Panzer Lehr Division documented 27 Panthers experiencing engine fires during forced marches to counter the Allied breakout from Normandy, not from enemy action but from fuel system failures. Crew ergonomics further undermined battlefield effectiveness. The gunner's position, designed by Rheinmetall engineers, featured a sophisticated targeting system with 2.5x magnification Turmzielfernrohr 12 gunner's sight, technically superior to Allied counterparts. However, the cramped layout required gunners to contort into unnatural positions during extended operations. Combat efficiency studies on tank ergonomics showed accuracy declining by 35% after 4 hours of continuous operation. Panther crew commander Otto Carius noted in his memoir, "The gunner's position became unbearable after long periods in combat readiness." Manufacturing inconsistencies compounded these design flaws. When Albert Speer's ministry mandated production increases from 250 to 600 units monthly in late 1943, quality control suffered dramatically. Metallurgical analysis of Panthers recovered near Kursk revealed inconsistent armor hardening. Some plates shattered upon impact rather than deflecting shells. This occurred because hardening processes required 12 hours of controlled cooling, but production pressures reduced this to 5 hours, creating stress fractures throughout the armor structure. The drive wheel interlock system designed by Professor Ernst Lehr illustrated how innovation could become liability. His interleaved wheel design reduced ground pressure to 0.88 kilograms per square centimeter, theoretically excellent for mobility. However, Eastern Front operations exposed fatal flaws when mud and ice accumulated between wheels, freezing overnight and immobilizing entire battalions. General Hermann Balk reported losing 19 Panthers in a single night near Korosten, not to Soviet action but to immobilization from frozen suspension systems. During Operation Citadel in July 1943, the 4th Panzer Regiment deployed 200 brand-new Panthers, yet by July 10th, only 38 remained operational, with 131 suffering mechanical breakdowns before even engaging Soviet forces. Similarly, during the Ardennes offensive of December 1944, Kampfgruppe Peiper's advance was significantly delayed when 35 of its attached Panthers developed transmission failures during the critical first 36 hours, forcing commanders to abandon their timetable. Perhaps most telling was the experience of the 9th Panzer Division near Metz in September 1944, when an entire company of 14 Panthers became stranded with failed final drives after a 35-kilometer road march. All were subsequently destroyed by Allied aircraft before they could be recovered. Ultimately, the Panther represents a case study in the difference between theoretical and practical superiority. While its 75mm KWK-42L/70 gun could penetrate 124 millimeters of armor at 1,000 meters, outclassing any Allied tank, this advantage proved meaningless when combined with a 43% operational readiness rate documented by Inspector of the Armored Forces in June 1944. As Inspector General Guderian concluded, a technically superior tank that cannot reach the battlefield represents the most expensive form of military failure.